Next up in this video, we're going to define a very important operation for matrices, and it's matrix multiplication, not to be confused with scalar multiplication. Scalar multiplication implies that you're multiplying by a constant. Matrix multiplication implies that you're multiplying by a matrix, right? So before I give you the formal definition for matrix multiplication, I want to present just a really simple example that will give us at least a justification for why we might even want to define matrix multiplication in the way that we will. So let's say I have two matrices, and the first matrix, they're both going to be 2 by 2. And this one matrix will be 2 by 2, another matrix will be a 2 by 1. Now in the 2 by 2, I'm going to use this array to store the amount of a certain product that different stores sell. So for instance, I'm going to keep the store information will be by row, right? And so store B, and then let's say in the columns now it will be what product. So product A there and product B in the second column. So let's say store A sells 20 units of A and 40 units of B, and then store B sells 30 units of A but only 10 units of B, right? So again, remember, we can use these arrays to store information. Now what I'm going to do is use another array to store another type of information. Now what I'm going to store in this matrix is going to be the unit price for the different products. So in the first row right here, I'm going to store the unit price of product A, right? And then similarly in this position, I'm going to store the unit selling price of product B, right? And let's say A sells at a price of, say $3 per unit, and then B sells at a price of $5 per unit, right? So then here is the question: what is the total sales, right, for each store? So how much money in total will each store make, right? Well, it sounds like there's some multiplication that needs to be done. So for instance, for store A, it sells this amount of product A at a price of $3 per unit, and it sells this amount of product B for this price per unit, $5 per unit. So yeah, if I wanted to, for instance, store this information in a new array, somehow I would have to figure out a way to multiply these two. But I can't just multiply them in any old haphazard way. Thinking of what it is I want to find, the total sales for each store, it's like I would have to take this row, which stores the information for store A, and somehow multiply this column, right? Which holds the unit price. And then similarly, I would repeat the process for the second row, multiplying this one. So somehow it seems like we would need to do something like this, right? So now that I've told you what the different things represent, stores this way, amount of product sold by each store that way, and then the unit price there for product A and there for product B. But let's strip away the labels now and just write down this array. And again, it would have to be some kind of product and then times that array. And just at the top, I'm going to indicate the dimension of each, right? So this one would be a square matrix, right? Because it has the same number of rows and columns. So 2 by 2. And then this one is kind of a special one. It has 2 rows, but only 1 column, right? And sometimes these are called, so when it has just a single column, sometimes it's called a column matrix or vector, which that word just seems to come out of nowhere, but it's going to be here for the long haul. But anyway, right? So somehow we would have to figure out a way to multiply these. But what we're saying is now, if we were to take, let me go back up just a little bit, the information, right, in terms of the amount of product of each product sold by store A, and then do this kind of pairwise product. So for instance, if I took the 20 times the 3, that would give me the total sales just for product A. So if I did 20 times 3, and then if I were to then do 40 times 50, that would give me the total sales for product B, but I want the total sales overall for the entire store, so then I would have to add these two together, right? And then similarly for store B, I'd have to take, again, how many units of product A it sold times the unit price for A, and then the sales, right? So that would be the total sales for product A from store B would be 30 times 3. And again, I'd have to add to that the sales from product B from store B. So that would be 10 times 5, right? So it's like what I would do for store A, I'd have to take information in that row and multiply it this way. Kind of do this pairwise multiplication and then adding things together. And then similarly for store B, I would have to take that information and again multiply, but in this weird way, those entries. So this times this plus this times this. So the end result is, look at what we end up with. We end up with another array. So this is 60 plus 200, so that's 260, and then 90 plus 50, that's 140. And remember, this corresponds to store A, this corresponds to store B. So this number right here now is the total sales from A, right, of A, and then this number here represents the total sales of store B. right? And notice what we end up with. Somehow we end up with another 2 by 1, which is kind of interesting in its own right. So this is again a matrix that has only 2 rows and 1 column. So this is another 2 by 1. So this idea, again, let me go back up here. So this idea of taking the entries in the row of the first matrix and multiplying, columns in the second matrix, that is the concept that is used to define matrix multiplication. All right, so we're going to write it down now, but before I write down the formal thing, well, everything that I'm about to write down is fairly formal, but the first thing I'm going to write down is that using the expanded form of the matrix to show you exactly what's going on, right? So it's a lot of letters, right? But it helps to kind of give you a motivation as to why, this matrix multiplication is defined this way. Okay. So what I'm going to do is, so A is going to be an M by P matrix. Well, actually, I shouldn't say is equal to. Actually, what I can say is, let's say the dimension of A, there you go, is M by P. And then the dimension of B is P by N. Right? So I'm going to write down a general matrix like this, a general matrix with these properties, and then show you what the product looks like, and then write down the definition. So here is A, so I'll use the little a's. So for instance, this will be A1, 1 as usual, A1, 2, and I'm going to skip ahead right here. Now remember, this goes out to P columns. So this will be A1P. But what I'm going to write down here is, well, yeah, let's do the dots there. And then I'm going to do A21, A22, and then A2P. And then this goes down to M rows. So the last row starts with the A, M1, A, M2, A, MP. Now what I'm going to do is write down a special row that represents the ith row. So I'm going to put somewhere in the middle. So it's going to be a there, It's like Morse code, right? But it's like this. And then essentially I'm going to write it in a different color so it really stands out. So this will be AI1, AI2, and then AIP. And this is what we're going to call the ith row of matrix A. Right, so just kind of the general. So if I is equal to 1, it would be at the top here. If I is equal to M, it would be at the bottom here, but this is the ith row, right? Now let's write down B. Now remember, B is a P by N. So it has P rows and N columns. So let's write that down. So again, you'll have like, I'll use B's now, B1, 1, B1, 2, and then it's going to go all the way out to B1N because it has N columns. So B1N. And then similarly, you'll have your B21, B22, and then now this goes down to P. So BP1, BP2, all the way across to BPN. Now what I'm going to write down isn't the general row, but now the general column here. So somewhere going down, I'm going to write down the jth column of B. Now let's do that in a different color. So for instance, this would be like B1J and then B2J and then dot 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 B P. Oh, this B looks like a P. Let me write that more clearly. So B P J, right? And you have your dots there. So this is the jth column of matrix B, right? And basically what we did earlier with the store and the unit price, where we took information in a row from in the first matrix and multiplied it by a column. Well, now we're going to have several columns to multiply, and the whole idea is this: we are going to if we did this particular pattern, right, and take the ith row of the first matrix and do that special multiplication and then addition with the jth column of the second matrix, that sum that we get, that single number, is going to go into row I, column J of the product, right? So let's write down what the product would be. So let's say when we multiply these, right, we're going to get a matrix of a particular size, and I'll tell you what the size is in a second. But more important, well, equally important, is how do we fill it out? So I'll put a little equal sign to say if I take this matrix and multiply this matrix, to figure out what goes in row I, column J, we have to take that blue row and do that special product with that red column, add them together. So what we're going to do is take this entry and multiply this entry, multiply this entry, and so forth. The last entry in the row will multiply the last entry in that column and then add them all together. So what I'm going to do is use another letter now and call this Cij, and Cij is formed by, so where Cij is equal to this. Again, take the first entry in the blue row and multiply the first entry in the red column. So you're going to have AI1 times B1J, and then add to that the second entry in your row times the second entry in your column. So then plus AI2 times B2J, and continue that pattern until you get to the last entry in the row and the last entry in the column. So then plus AIP times BPJ, right? And that's how we're going to define the product. So it's this strange product where you take rows from the first matrix and multiply columns, multiply and add corresponding entries in the columns of the second matrix and add the terms together. And you use that to fill out this new matrix, right? So I'm not going to write the other C's. I just wanted to highlight how you form a particular row, a particular entry in this product, right? So let's write it down. right? So here is the definition of matrix multiplication. And then I will say something about this particular product, right? So if A is an M by P matrix, and B is A should be AP by N matrix, the product of A and B, so the product of A and B, and how do we write it? Well, the same way we do, multiplication. We use juxtaposition. So A, B is the matrix. So let me write like that. So I'm going to call it C. So when we multiply A and B, we're going to get this matrix. We're going to call it C. And C is going to have this dimension. It is going to be an M by N matrix, right? So C is the matrix AB with dimension M by N and entries defined by this rule. So, and entries defined by Cij, and it's this exact same thing that I wrote down. So it's going to be AI1 plus B1j plus AI2 times B2j plus dot dot dot, and then AIP times BPJ. And the thing is, we can actually use sigma notation to write this down. So it looks like this. So if you notice, what the I and the J are, they're always there. So the I is there, the J is there, similarly there and there. But what changes is the one that's here, it changes to a 2 and then eventually to a P. So we can write this in sigma form, noticing the pattern. I'm going to use K as my index, so a third letter, but K will go from 1 to P, so starting from 1, ending at P, and then you're going to take the AIK entry times the BKJ entry and sum those up from K going from 1 to P, right? So whether you can visualize the sigma form more clearly, or you prefer seeing it written out like this, this is the formal definition of matrix multiplication. But in principle, if we go back to where we started with that example with the stores and how much product they sold and what was the unit price, if we just go by that idea of multiplying rows and columns, then we don't necessarily have to rely on this very formal definition that can seem overwhelming, right? So to do that, let's look at some examples. All right, so let's look at a couple examples. And let's start with two 2x2 matrices. So let's say A is 2, -3, 4, 5, and B is 1, -1, 8, 2, something like that, right? So let's see if we can use this particular formula or process, right? Think of it more of a process rather than a formula that just seems really abstract. But let's see if we can write down the product A times B. Now, what is sometimes lost until you really get used to it is the fact that the in order for matrix multiplication to be defined, remember what the definition says. I'm not going to scroll back up, but I'm going to remind you. It says that A has to be like an M by P matrix, and B has to be a P by N matrix. So what that means is these two numbers must be equal for the product AB to be well defined. So these must be equal, right? And then it also says that the matrix C that we're going to get, the product of these two, is going to be an M by N matrix. So these pairs of numbers, they not only tell us when we can do the product, but they also tell us what the dimension of the answer is going to be, right? So the fact that the first matrix has two columns and the second matrix has two rows, this tells me that AB is well defined. And then the remaining two here and the remaining two here tells me that the answer is going to be another 2 by 2. All right. Well, let's see if we can follow our process. Right. And again, I'm just going to say it out in words. But if I want to figure out what entry goes in position A or position 1, 1, so first row, first column, I have to take the first row there and then do that special product with the first column here, right? So I have to take this, so I'm going to write it down. I have to take 2 times 1, right, plus negative 3 times 8. Right? And that is going to be the entry in the first row, first column. So if I take the first row times, now when I say times, I mean this special pairwise multiplication and then adding up those terms. So I have to take the first row times this first column, right, and then take the sum, right? So first entry here in that row times the first entry in the column, and then the second entry in the row times the second entry in the column. That's why these two numbers have to be equal, because if they're not equal, you won't be able to match them up pairwise, right? All right, so that's that one. So now let's say we want to do, so let's finish out the first row in our product. So now I will repeat the process using again the first row, but then use the second column, right? So I'm going to take 2 times negative 1 and then plus negative 1 times 2. Negative 3 times 2, sorry. Negative 3 times 2. And then that will close that bracket, right? Now let's switch to the second row. So it's first entry in the second row times the first entry in the first column. So 4 times 1. And then plus 5 times 8. So 5 times 8. And then finally now to figure out what goes in the second row, second column, I have to take the second row of my first matrix and do the special product with the second column of the second matrix. So that's 4 times negative 1 and then plus 5 times 2. So we can see we're going to get another 2 by 2, and now we just have to fill in our entries. Right? So what do we have here? 2 minus 24, that's negative 22. Negative 2 minus 6, that's negative 8. 4 times 40, that's 44. And then finally, negative 4 plus 10, that's a positive 6. So that's our product of A times B. What if we switched it around? What if we did A, instead of A times B, what if we did B times A, right? So if we took B times A, and just to help us keep things organized, I'm literally going to write back what B is, what A is, and then do the product, right? So that way we can keep track of the rows, because we have two sets of numbers to keep track of now, rows and columns. So there is B, and here is A, 2, negative 3, 4, 5. It's still a 2 by 2 times another 2 by 2, right? So again, if we just do that little check to make sure that what we're about to do is actually well defined, again, these two numbers tell me that yes, because they're equal, the product is well defined, and then the answer, again, is going to be another 2 by 2. All right, so let's write out these expressions first so we can see everything that goes into forming this product, and then we can simplify. All right, so I'll scroll all the way down since I have rewritten the matrices. Okay, so let's see what goes in the first row, first column. So I have to take the first row of B now and multiply the first column of A, and it's the corresponding position. So first entry in the row multiplies the first entry in the column, and then add to that the second entry in the row multiplies the second entry in the column. So like that. So that entry is fixed. Now again, let's finish out that first row. So again, take your first row, but now repeat the process with the entries in the second column. So 1 times negative 3, right? So first term or entry in that row times the first entry in that column, and then add to that the second entry in the first row times the second entry in the second column. So negative 1 times 5. And then I close it. Now repeat with using now the second row of B. So 8 times 2 plus 2 times 4. And then finally now let's finish it out. So or the last entry in our product is 8 times negative 3, and then plus 2 times 5. Right? And then let's simplify like we did above. So we have 2 minus 4, that's negative 2. We have negative 3 times negative 5, that's negative 8. We have 16 plus 8, that's 24. And then negative 24 plus 10, that's negative 14. And one thing you might notice right away, and this is often, sometimes it's like disturbing for students to see this, but look at the matrix AB. The only entry that corresponds in BA is this entry. All the other entries are different. So what this little example shows is that even though both of these products are well defined, they're not equal. So the order in which we multiply our matrices, it affects the answer. And that is shocking because we're always told, oh, the order in which you multiply doesn't matter. Well, for numbers, that's true, but not for matrices. So this is huge. This is like, earth-shattering. So note, AB is not necessarily BA. And what this means is matrix multiplication is not commutative. All right, so matrix multiplication is not commutative. So we can't take it for granted now that the order, we can just switch the factors around, commutative, and get the same answer, right? So just think about that for a little bit. It just shows you that when you start doing algebra with different objects, you may lose some of the properties that you're so used to that you don't even think about when you use them. You just take it for granted that they exist. But as you go from one system to another where the rules might slightly change, then those properties might no longer exist, right? Now, in this example, we were actually able to compute A and B. Let's look at a last example and show, so let's do something like, let's do a 3 by 2. Right? And then let's do like a 2 by 4 maybe. So let's say B is, let's say 1, 1, negative 1, 0, 2, 3, 4, 1. All right. So I want you to see what it looks like when we do this operation with non-square matrices. So let's see. So this is a 3 by 2 matrix. This is a 2 by 4 matrix. And these two numbers, it tells me that the product is well defined. If I put A first and then multiply B, I can do it. And then my answer is going to be a 3 by 4 matrix. All right, let's see what that looks like. All right. So A times B. So since they're already written in that particular, A is here, B is here, I'm not going to rewrite them. Let's just write down the different entries, right? Now, there are 12 entries that we're going to have to write down because it's a 3 by 4. Okay, so let's see. First row, first column. So that's 3 times 1 plus 1 times 1. First row, second column. That's 3 times negative 1 plus 1 times 0. First times third. So 3 times 2 plus 1 times 3. And then first times fourth. That's 3 times 4 plus 1 times 1. And then we can close it. Then we rinse and repeat, right? So second row, again with each of those columns. So we will have negative 1 times negative 1 plus negative 4 times 1. And then negative 1 times negative 1. So now I'm using the second row and the second column. And then negative 4 times 0. So negative 4 times 0. And then second row, third column. So that's negative 1 times 2. And then plus negative 4 times 3. And then finally negative 1 times 4 plus negative 4 times 1. All right, and then last, so third row again with each of the columns. So 1 times 1 plus 8 times 1. Then 1 times negative 1 plus 8 times 0. And then 1 times 2 plus 8 times 3, and then finally 1 times 4 plus 8 times 1. All right. Well, let's write down the final answer. So what do we have here? So we have 4 and negative 3, and then 6 plus 3, that's 9. 12 plus 1, that's 13, and then I can close it. And now negative 1 plus negative 4, so this is negative 5. And then 1 plus 0, so that's 1. Negative 2 minus 12, that's negative 14. Negative 4 plus negative 4, that's negative 8. And our final row, 1 plus 8, that's 9. Negative 1 plus 0, that's negative 1. 2 plus 24, that's 26. And then 4 plus 8, that's 12. Right? So that's the product of A times B. Now notice, if I tried to do B times A, right? So I'm just going to do that here. I'm going to break this off. So if I tried to do with this pair of matrices, if I tried to do B times A, well, B is a 2 by 4 matrix, and A is a 3 by 2 matrix. And because these two numbers are not equal, I could not do the product in this order, right? So this is undefined. And it's not just that the dimensions are different, because look, these dimensions are different. But what happens is the first matrix, the number of rows in the first matrix is equal to the number of columns in the second matrix. That's not the same here, right? So this is undefined. Because the number of columns of B is not equal to the number of rows of A, right? So again, what this example shows you that it's not just the fact that dimensions are different. That's not a sufficient explanation. The explanation has to do with exactly how many columns are in the first matrix in your product and how many are in the second, right? So these two examples, though fairly simple, think through them, maybe work through them on your own again, and verify the calculations, but more importantly, it just shows the difference of multiplying two numbers versus multiplying two matrices. In fact, sometimes the product of two matrices is not even defined, as we saw right here, right? So that's the interesting operation of multiplying two matrices, and you might be wondering, well, what else can it be used for, right? I gave you one simple use in terms of, products sold and unit price, but that concept actually can be extended to many other applications, right? So things to look forward to. See you in the future.